All right. Well, thank you all for joining today. Thank you for taking time during your lunch hour to come listen to me. I'm going to be talking about, as the title of the presentation shows, some data analysis gotchas and the importance of statistical reasoning. I think the main theme in here is going to be careful. Most folks here, it looks like, are data analytics students. I see a few data science students, and so we're the types of people that like to get into a data set and see what you can find and explore it and ask questions. We interview everybody who comes in for a data analytics bootcamp, and one of the things that we ask about is why are you interested in working in data or doing analytics? And most people say it's a lot of fun. I like the idea of being able to come up with recommendations, get some concrete evidence of things, generate insights, find things that people haven't seen before. And that is a lot of fun, and it's a neat idea. A lot of companies have realized that data is kind of booming now, and has been in the last decade or so. Companies are collecting a lot of data, and sometimes just storing it and saying, boy, it would be nice if we had some people that could come in and tap into this and come up with some insights for us. Companies, they want to be data driven. They want to let the data speak for itself. You use evidence-based decision making rather than just going off of intuition or kind of gut feelings, or it's what we've always done. But it is important to be cautious when you're making recommendations, or when you think you found something in a data set. Like, we can't be too cavalier in, you find something interesting and let me share that out. There are some gotchas, some traps you can fall into. Some of them are obvious, some of them are not so obvious. And so it's important to look into any takeaways, either that you come up with or that other people come up with. It's important to look at those things with a critical eye. And so, where do these types of problems come from? I think part of it is that humans are just really, really good at detecting patterns. So people theorize that it's part of our evolution, that we're really, really good at spotting predators, spotting these plants are poisonous, these plants are healthy. So anything that you can help you survive is probably going to get passed down. And so this is useful in some cases, because you can make decisions very quickly on the fly. You don't have to look at or memorize all of the data. You can develop some rules and either consciously or unconsciously, and then rely on those rules, rather than having to expend a whole lot of brain power. But this does have a drawback in that sometimes you can find patterns or think that you spot something when there's not really anything there. For example, just as kind of a fun example, back in the 70s, NASA had a Viking project, and they sent spacecraft out to Mars, and they landed on Mars. And part of that, they were collecting a lot of photographs, photographing the surface of Mars. And so as these were coming back in, people were pouring through the different photos of the surface of Mars and seeing what they could find. And there was one particularly interesting photograph that came back. And people looked at it and they said, hey, wait a minute, that looks kind of odd. Is that ET up there? Is there extraterrestrial life that has put this face up there on Mars? Of course, once they went back and got better, higher resolution images, then it turned out it was just a regular old mesa. I think it would be the technical term for that, and just the light sort of illuminated in just the right way. But our brains, they're sort of looking around, and particularly for faces, but things like that. So you can potentially see or think you see something there when there's not really anything there. This is not a particularly nefarious example or anything, but another place where that pattern recognition can go haywire would be if you, not that I necessarily recommend you go play roulette or anything like that, but if you step into a casino, there's the game of roulette, essentially a wheel with 37 or 38 slots on it, depending on how much they want to rip you off. And drop a ball in, and you can bet on where you think the ball is going to land. The casinos are very, very nice. If you go to a roulette table, then they'll actually they have these displays that show you, here's the last dozen spins, here's where it landed. They tally it up for you. Oh, this wheel lands on red 46% of the time and black 49% of the time. And so they're relying on what's called the gambler's fallacy, where it just feels sort of naggingly like if I can analyze this data, I can get an edge. This one, it's been landing on black a whole lot recently, maybe I should bet on red because red is due, or vice versa. Maybe, oh, black is coming up all the time, maybe I should bet on black, when really these are completely independent draws. There's no patterns. You wouldn't be able to gain any edge in using that data. So this one, potentially, and sort of casinos are counting on at least some folks to get that nagging feeling that, oh, I detect a pattern, I'm gonna start wagering one way or the other. Face on Mars, maybe not so bad, but how do we try to navigate these situations? How do we know, or how can we make sure that our pattern recognition isn't going overboard, we're not seeing faces on Mars or whatnot when we're looking at a data set? And so this is where statistics and statistical reasoning come in. Essentially, statistics is a set of tools for how you can approach collecting or analyzing or arriving at sound conclusions from data. And also, part of that is avoiding jumping to undue conclusions. So coming to conclusions or recommendations that the data doesn't really warrant. So I'm gonna talk today about 3 cases of situations where someone came to a conclusion using data and seemed like a reasonable conclusion, but they actually made some sort of fundamental mistake in their reasoning that could have been avoided if they had really sat down and thought through the situation like a statistician would. And then I'll give you some tips for how can I prevent myself from making similar types of mistakes. And a large part of it is just being aware of the fact that you could be making a mistake, and saying, let me pause for a minute and think through this and make sure that I'm not overlooking something important. All right, so this is going to be 3 parts. So part 1 is about the missing bullet holes, and so part 1 is going to take us to 1943, and this was a couple years into America's involvement in World War II, and a major part of America's offensive in Europe was strategic bombing. This was done by the United States Army Air Forces. So this was before the Air Force was a whole separate branch of the military. But the idea was fly in there, take out factories or shipyards or steel mills, things that were important for Germany's war machine. So of course, Germany is not going to just say, all right, come on in and blow our stuff up. They're gonna put up some defenses, including things like this anti-aircraft gun here, this 88 millimeter anti-aircraft gun. So in response to these bombers coming in, Germany had their defenses. They were doing their best to shoot down these planes. And the U.S. military had been losing a large number of these bombers. You'd send them in, they'd get shot down. And so military was trying to come up with, what can we do? How do we stop losing all our bombers? how do we prevent them from being shot down all the time? And so the idea, was, well, let's add some more armor onto these things, so that they could absorb some more bullets. Problem is, armor's heavy. You can't very well armor the whole plane. You kind of have to prioritize, where am I going to put this heavy armor on the planes. It's you got to carry fuel, you got to carry ammo and bombs and pilots and all that. And so if you armor like the whole thing, you're not going to be able to maneuver. You'll have a really, really safe plane, but you won't be able to carry any bombs. So you can't carry out the mission. It's kind of a nice, like, classic data analytics kind of problem. We have sort of some limitations here. You have these constraints. We have like a limited armor budget, and we got to know, how do we get the most bang for our buck? Where do we place the armor so that we have the greatest chance of success? And so what the military decided to do was, let's gather up some data. Let's look at the data and use that data to inform our decision. And so what they did is, a plane would go on a mission. When the plane came back, when it returned from the mission, they inspected it, they looked it over, and they said, where did this plane get shot? Where are the bullet holes on this plane? And so, once they had gathered enough data, seeing where do planes tend to get shot, the decision was, that's where we're going to put the armor. So, you might end up, this is not the actual diagram, but if you tracked it out, it probably looks something like this in terms of where they tended to see bullet holes or not. So in looking at the data, it looks like these planes tended to be shot kind of in the middle here, like along the fuselage, maybe at the ends of the wings or in the tail. And so, since this is where these planes tended to get hit, the idea was, well, let's put the armor there. I only got so much armor. We're going to put it in the areas that tend to collect bullet holes. But fortunately, before committing to that decision, the military said, well, let's bring in some other folks and get their opinion on it. And so the military, they turned to the Statistical Research Group, which was a research group at Columbia University. And this group was focused on military application, military problems. And in this group was Abraham Wald. He was a Jewish-Hungarian mathematician. He was a brilliant guy, young mathematician and statistician. And he had come to the U.S. actually in 1938 after Nazi Germany had annexed Austria. Abraham Wald, he took a look at the data that the military had gathered, and he said, you all have decided you want to armor these parts of the plane. Well, actually, what you should be doing is you should be putting armor in the other places. You should not armor where you're seeing bullet holes. You should actually armor over here, like in the engines in particular, or the areas where you are not seeing bullet holes. So, how did he come up with that, or what did he do? Well, he made the critical realization that in this case, the important data was not the data that they had. The data they had was planes that had gone out, had completed missions, and had come back. But the important piece here was actually the planes, the data they didn't have, the planes that did not return. So we're trying to prevent these planes from being shot down, and we're missing the planes that got shot and didn't make it back. And that's the important thing. So he realized, like, it doesn't really make sense that these planes would be collecting bullets more densely in one area or the other. They're probably getting shot, more or less the same across the whole plane. And it's got to be the case that there are certain areas that if you get shot here, you're going to be more likely to not be able to make it back to the base. So key realization: the data set collected was an incomplete sample. And so you should actually armor the areas where the bullet holes are less dense, not more dense, because those are going to be the areas where if you get shot in these areas, you're going to be more likely to not survive. And so he did some fancier math than just that, and came up with some estimates in terms of in these areas, your chances of not surviving is this much versus other areas. But anyway, his realization, or his recommendation, was the engines that's going to give you the lowest chance of surviving. And so what happened here, or what type of error was committed? This is actually like the classic example of what's called survivorship bias, where you're looking at entities that pass through some sort of selection process, and you are overlooking those that did not make it through that process. So here it's sort of quite literally, we have some planes survived, which is the ones that we have data for, and then other ones didn't make it back, and we don't have the data for those. And so it's very important, to think about when you're looking at a data set: is there some form of survivorship bias here? Do I have a sample that represents the full population, or at least the portion of the population that I care about, or is there some mechanism that is preventing me from seeing the data for some portion of that population? So some other examples of survivorship bias: mutual fund performance is another kind of classic example of survivorship bias. So if you were to look back, if maybe you're interested in which mutual funds performed best over the last decade, and you looked at the data and you were tracking, what's the average performance of a mutual fund over the last 10 years, then if you did that, you would likely end up with an overly optimistic estimate, because with mutual funds, not all mutual funds are going to make it. Some mutual funds are going to fail. Probably the ones that are going to fail are going to be the ones that that didn't perform as well. And so the ones that are still around after a decade are going to be ones that had at least reasonable performance. And so, for things like that, where potentially people have the possibility of failing and sort of dropping out of the population, make sure you consider that. Another one, if you're looking at appliances or buildings, sometimes people will say, oh, they don't build houses like they used to. Like if you look at a house built in the 50s and that thing is rock solid, and they just slap them up nowadays. That sounds reasonable, because it's true. If you go into a house that was built in the 50s, it probably is pretty darn solid. But the problem with that reasoning is that if you're looking at a house that was built in the 50s, it probably had to be built pretty well if it's still standing nowadays. So in terms of the sample that you have, the ones that are still around by necessity are going to be the ones that are built a lot better. Another case: movie stars or athletes or musicians or CEOs, people that are highly successful. Sometimes people say, well, let's look at the, what did Mark Zuckerberg, what did Bill Gates do? Well, they dropped out of college. So if you want to be successful, drop out of college. But that's probably not good advice. So if you only consider those at the top, and you ignore everybody else who did similar things to what they did, and you don't consider that there is some element of luck in that, then you could be falling to survivorship bias in your recommendations. So in terms of advice to avoid a survivorship bias, think carefully about the source of the data that you're working with. Think about, what might be missing. Is there anything that could be missing? Is there some selection process that prevents me from having access to the entire population? And just in general, is the data representative of the whole population of interest? So for Abraham Wald, realized the planes that we're looking at, that's not representative of the whole population because it does not include the planes that didn't make it back. And actually, in this case, the planes that didn't make it back are actually the ones that hold the important information that we need. All right. So survivorship bias is one thing to be aware of, and just sort of bias in general, making sure that the data that you're working with is representative of the population of interest. Part 2 is going to take us to the the misguided development, I'll say, of the long ball strategy. So for this part, let's start with these two gentlemen here. And some of you may recognize these two, or maybe you don't. But if I show you this one, maybe you would recognize these two guys. So this is Brad Pitt, and who is that? Is that Jonah Hill? Jonah Hill, I think, yeah. So they were playing the gentleman on the left here, Billy Beane, who was the former general manager of the Oakland Athletics, and then Paul DePodesta, who is he's currently with the Cleveland Browns. He's the chief strategy officer, but he was a front office assistant for the Athletics. And so they, as made famous in the book and the movie Moneyball, Oakland Athletics, as they still are, they're sort of a low budget team. They didn't have the payroll that teams like the Yankees had, or the Dodgers, or some of these big market teams. Oakland Athletics, they had to try to get by with a payroll that was about a third of the size of the Yankees. And so Billy Beane and Paul DePodesta, they famously developed what's been termed Moneyball, where they were applying data analysis, or sabermetrics is the fancy term for data analysis to baseball data, but they applied that and were looking for attributes of players that had been overlooked. Famously, on-base percentage was the thing that they realized was being undervalued. It's not necessarily that on-base percentage is the end-all be-all, but teams were undervaluing on-base percentage, and so they were able to snatch up some bargains in terms of on-base percentage, and they were quite successful in the early 2000s with that strategy. And so these two kind of brought a lot of these analytical principles into the mainstream, and nowadays their legacy has carried forward. Things like the infield shift, which have been around for a while, but up until recently, when they've adjusted the rules for it, then it was something that teams started doing very, very frequently. They would track where does a batter tend to hit the ball, and they would position the fielders based on those tendencies. They track just about anything in baseball. They'll track the spin. When the pitcher throws the ball, they'll track the spin on the ball. And kind of interestingly, last season in Major League Baseball, there was kind of this scandal going on, or I guess you would call it a scandal, where pitchers were using this foreign substance, this sticky stuff is what they called it, allow them to get a little bit better grip on the ball, and give them basically an unfair advantage. And so you started cracking down on that. But actually, if you went back and looked at the spin rates on the balls, then that could be one way that you could detect who was using this sticky stuff, because the spin rates would be just outrageous compared to their normal spin rates. And this is gone beyond baseball, and in the NFL. A lot of teams are relying on analytics and expected points and figuring out, should I go for it on a fourth down or not. So sports is great for data analytics. There's just so much data there, and it's just a really fun venue to look into these sorts of things. So anyway, Nowadays, it's easy. We got cameras everywhere. We can store just anything that you want to store. You can, but that wasn't always the case. So if we go back to the 1950s, let's go to London in the 1950s. This was post-war at this point, and so people are looking for entertainment, and soccer was one popular form of entertainment. Now, at that time, people weren't tracking the soccer stats or strategies, or coming, applying analytics to soccer. There was hardly any of that sort of thing going on. Enter Charles Reap. So Charles Reap was wing commander in the Royal Air Force. He was an amateur statistician, and he was a soccer fan. And the story goes, I don't know if it's true or not, but the story goes, he was watching a match in 1950, and he was like, "Man, this is so slow. These people don't know what they're doing. Like, this is painful to watch. I'm gonna come up with a better strategy for these soccer teams." And so halfway through the game, he brought out his notepad, and he started taking notes, and was just methodically tracking passes and shots and positioning and that sort of thing. And he did that throughout the rest of the season. And so he gathered up a whole lot of data. Based on this, he was going to try to come up with a better strategy in soccer. How can a team be more successful? He wanted to know, a couple of things. He wanted to know, how many goals do you need to be successful? And maybe more importantly, how can you give yourself the best chance to score that many goals? Or how can you give yourself the best chance to score more goals? And so, based on the data he was collecting and tracking, he had some findings. He determined teams typically scored about 2 goals. And so, he thought, well, if we could go from 2 to 3, you could just increase it by 1. You got a good chance of being successful. He said, well, you need about 10 shots to get 1 goal. So you got to generate a lot of shot opportunities. Another thing he found was that most goals in soccer were scored on plays where there were fewer than 3 passes. And then he also found that half of the time goals came from breakdowns in a team's own half of the pitch. So basically, like, if you're passing it around and you turn it over, the other team can pounce on that and score quickly. But the big thing that he latched onto was actually this third one here. Most goals were scored from fewer than 3 passes. So based on that, based on the data he had collected, and when he had analyzed it, he came up with some recommendations. His recommendations basically came down to, in soccer, efficiency is key. You want to create as many chances as possible. If you can get the ball near an opponent's goal, that's going to lead to more goals. The big thing he hammered on was keep passing to a minimum. If most goals come from plays that have 3 or fewer passes, don't be passing it around just for no reason at all. Keep passing down to a minimum. And he kind of hammered on 3 or fewer passes. Like, you shouldn't be doing these long plays where you're passing it back and forth. And so he sort of took this to an extreme as well. And he said, really what you should be doing is just get that ball forward as quickly as possible. So, have somebody just boot it all the way down the field, get it to the forwards up near the goal, and then they try to kick it in. And so this strategy is nowadays called the long ball strategy, but it's basically kick the ball down to the goal just as quick as you can, and then make a shot, and then just repeat that. If you don't make it, that's okay, because it takes about 10 shots before you get a goal, but just generate as many of these opportunities as you can. Forget about all that fancy, dribbling around and passing it. Just go straight for the goal. And so this was adopted. A lot of teams in England, listened to him. He gathered the data, he analyzed it. This is what he says. This is what's effective in soccer. And so teams adopted that, and for a while it was, very much in vogue. So teams were just, cutting out all that passing stuff, and it became a game of just kick the ball all the way down the field and then shoot, and then the other team gets it and they kick it all the way back and then they shoot. And it doesn't sound all that fun. It doesn't sound all that interesting. And a lot of people say that this guy killed the beautiful game because it's just cut it down to just like a shootout almost in England. But he was like very influential in English soccer, and for a long time, then that was how teams from England sort of designed their strategy. So how did this strategy hold up? Like, it sounds reasonable, based on the data. Yeah, just generate shots, don't pass it around a whole bunch. Well, sort of time showed that this wasn't really all that effective. People have gone back and done further analysis on soccer, and so there's a somewhat recent paper looking at 2018 World Cup, and basically greater number of passes results in increased likelihood of goals. So kind of exactly opposite of what he said. More passes, more goals. Other people have found it's really about like maintaining possession and effective short passes. So being able to make passes to the right part of the field to give yourself a greater chance of goal is more important than just get it down there and make a shot, any shot at all. So looking at like possessions per game versus shots per game, being like, rather than sort of like the Hail Mary, we just kick it down there and do what we can, being very careful of trying to avoid turnovers, trying to have a lot of possessions leading to more shots. So what he came up with, sounded reasonable given the data. And given what he found in the data. So where did he go wrong? What was wrong with Mr. Reap's reasoning here? And how can we avoid that same sort of mistake? So I guess the big thing and where his reasoning starts to fall apart a little bit. So his main conclusion, like the thing that he sort of latched onto, was that if we look at plays that resulted in goals, then most of those plays were ones where there were 3 or fewer passes. It was a very short sequence. But in soccer, if you watched any amount of soccer, then you'll know that most of the game, it's going to be short sequences. There's a lot of turnovers in soccer. One team has the ball, they'll make a couple of passes, and then the other team will get the ball and they'll make a couple of passes. So if we're just looking at all plays in a soccer game, it's going to be, most plays are going to be these short sequences. And so just because you say there's a goal, what was the length of the sequence? Well, it's going to be more than likely going to be a short sequence because most sequences are short. So he was asking the wrong question, basically. Instead of saying how often each type of sequence or each length of sequence preceded a goal, he should have said, how often does each type of sequence result in a goal? So if we have a short sequence, how likely is it that this sequence is going to result in a goal? If we have a long sequence, how likely is it that this sequence is going to result in a goal? So he was sort of looking at it backwards. And so just as an analogy, if we were trying to determine like how likely am I to get into an accident, or how does sort of snow, if it's snowing outside, how does that affect my chances of getting into an accident? And so if we were trying to answer that question in Nashville, and we were saying, well, let's look at, when do accidents occur? Or if we look at accidents that have occurred and we ask, for a given accident, was it snowing or not? Well, if we do that in Nashville, it's going to be almost all the time the answer is going to be no, it was not snowing when that accident occurred. And so if we were thinking like Charles Reap was, then we would, based on that, we would say, oh, well, you are, it's much more dangerous to be driving when it's not snowing than when it is snowing. So if it's snowing, it's fine, go out there, go ahead and drive, because most accidents happen when it's not snowing. So he was asking the sort of the wrong question, or asking the question in the wrong way. And this is the same sort of mistake that I see a lot of times on analytics capstones. I guess I could call this like the capstone error. But you know, a lot of times students will be looking at they'll have a data set where they're looking at something by state, and so it might be like COVID cases by state. And then they put it into a choropleth where they're showing like, here are the number of COVID cases for each state. You know, darker states have more COVID cases. And so if we looked at this, we would say, oh, gee, California, Texas, Florida, New York, they sure do have a lot of COVID cases in those states. Well, if I pulled up population choropleth, California, Texas, Florida, New York, you know, same things light up. And so we're you know, looking at this the wrong way. So we're saying, yeah, if there's a COVID case, how likely is it to land in these states? Well, yeah, it's going to be more likely than other states because there's a whole lot of people there. So what should we be doing? We should be normalizing. We should account for how many people are in each of those states, at least if we're going to make meaningful comparisons on here, and not just report where the people are. And so for COVID cases, for example, it's commonly reported as maybe, instead of the number of deaths, the number of deaths per 100,000 residents, something like that. And so that changes the picture. It's no longer just the states that have a large population that are standing out, but it's the ones that have a higher rate of deaths. And so, you know, how can we avoid this sort of mistake? You know, think about, do we need to normalize our data in some way? So by population, by number of plays. So in his case, he could have said, what proportion of plays result in a goal for each, you know, sort of length of play, or short plays versus long plays, what proportion result in goals? So normalizing for how often you're seeing each type of play. Or, you know, thinking about like base rates for the events that you're looking at. So you know, sort of the base rate for a short play is much higher than for a long play. They just happen way more often in soccer. And so are we, you know, considering that fact when we're coming up with our recommendations? So all right, I've got one more for you, one more thing to consider, and this one is based on something that has been dubbed the most dangerous equation. It sounds a lot scarier than it is, but it could, I guess it could kill your analysis if you don't consider it. So let's look into the most dangerous equation in one case where it got somebody. So for this one, we will go to the early 2000s, and so these two folks here, this is Bill and Melinda Gates, and so they've got a Bill and Melinda Gates Foundation. It's as of 2020, it was the second largest charitable foundation in the world. It had $69 billion in assets, just humongous. And so they have you know, all sorts of initiatives that they do, but one of the things that they focus on is expanding educational opportunities in the US. And so in the early 2000s, there was a big effort to shrink the size of schools. So the thought was, you know, large schools are not as effective as small schools, you know, for a variety of reasons. And so, you know, as much as we can, we should be focusing on smaller schools, breaking up these larger schools into smaller ones. And so, you know, you might say, well, what is the impetus for doing that? What's the evidence that works? Well, it was claimed that achievement improves when schools are smaller. And if you look at test scores or you know, other metrics, the achievement improves when schools are smaller. So how do we arrive at that conclusion? Well, if you look at the data and you look at top performing schools, you know, the ones that are very highest in terms of test scores, then what you'll find, and probably, you know, even if you pull up like Tennessee's data, there's a decent chance that the ones that are top performing are going to be disproportionately small schools. I think I worded this poorly, but there's a disproportionately large number of small schools. So small schools are overrepresented in the top performing bunch. And so that, that sounds good. It's like, okay, if the top performers are small schools, maybe there's something special about small schools. And so that, let's, as much as we can, let's push to make schools smaller. So they did that in the early 2000s. They attempted that, but it didn't take all that long. By the mid 2000s, it was clear that that was not really effective. And the foundation, in terms of their educational efforts, they moved away from this small schools movement to other efforts. And in their annual letter in 2009, they said, well, many of the small schools we invested in did not improve students' achievement in any significant way. So, well, what went wrong? What was wrong with their analysis? The data said top schools tend to be small, so why not invest in small schools? Okay, so this one is a little bit more involved than the previous one, so buckle up on this one. But this one, I think this was a really cool one, and once you're aware of it, it is you'll become very skeptical on a lot of things. So what was the mistake? So let's forget about schools for just a minute and just think about a different type of problem. So we'll go to like a toy example and think about just flipping a coin, just a regular coin, heads or tails. So imagine, we got a coin and we're going to flip it a whole bunch of times and we're going to track the number of times it lands on heads. And so, for a coin, it's 50-50 or as close to 50-50 as you can get. And so, what does that mean? Well, if I tracked, over a long string of coin flips, I would expect about half the flips to land on heads. But what about the short term? So in the long run, I'd expect about 50-50. But what about in the short run? Well, in the short run, I can use Python to help me kind of simulate some of these situations, but I've got a few simulations that I ran, but if I flip a coin 10 times, let's say, and I'll use NumPy library. I think most people are familiar with NumPy, which they've got some ways you can generate random numbers and whatnot. So I can use it to simulate coin flips. So if I flipped a coin 10 times, you probably wouldn't say that it would be weird if it came up 6 out of 10. That seems probably completely reasonable thing to happen. So that would be 60% of the time. It's not 50%, but it's 60%, and that seems within the realm of possibility. If I flip it maybe 25 times, it doesn't seem all that unusual that would come up heads 44% of the time. Or if I flip it 100, maybe 47, that's normal. So, in none of these am I arriving like exactly at 50%, but we're sort of close. And I think that all of these look like sort of reasonable things to expect. Now, rather than just flipping it and sort of tracking like one at a time, what I did is I used Python to kind of help me simulate a long string of coin flips. So this graph is showing what happened on one particular run where I flipped a coin 1,000 times, and as I was flipping it, I just tracked like what proportion of the time has it landed on heads, and so it starts out a little bit above 50%, and then it dips down, and then it goes back up, and then it dips down a little bit. But the kind of behavior that one might expect is that as I flipped it more and more times, the proportion is going to get closer and closer and closer to 50%. So in the long run, it's going to arrive at 50%, but in the short run, it wouldn't be unusual to be a little bit far off from that 50% line. And I can actually, with a little bit of math, I can even draw some boundaries here. And I'm not guaranteed that the proportion is going to land within these boundaries, but I can be pretty sure. So, on this run, we can see we were, again, like quite far at certain points, but in the long run, I ended up close to 50%. And, since I'm using Python and it can automate these things real quick for me, I can actually do that for like 100 runs of 1,000 flips. And And so each of these, it's a little bit hard to see because it gets quite crowded, but each of these is, one run of 1,000 flips. And I can see that over time it does get, they do tend to approach 50%. They do, there are some of them that bounce around, but for the most part, they sort of stay within these fences with a few exceptions. Okay, cool. So what? So how does this connect to schools? So let's forget about tests. Nobody likes standardized testing. Let's just do an experiment where we have each child in a school is going to flip a coin, and we're going to count the proportion that landed on heads for each school. Every student, get out a quarter, we'll flip it, and then we'll just record how many of those coins landed on heads for each school, and then we're going to see which school was best at flipping coins and them landing on heads. What schools ended up with the highest proportion of heads. Which schools would we expect to have the highest proportion of heads? Well, when it comes to this situation, I'm no longer doing what I did here, where I said, well, I'll do strings of 1,000 flips all the time, and then I always end up close to 50%. For each school, I've got different numbers of students. So it might be like a medium-sized school is only going to have 500 students or so. And so by the time they get done, I haven't made it all the way to the end here. I've got this run that sort of stops in the middle. Now, for a larger school where I've got like 1,000 students, maybe their run ends up here, close to 0.5. And maybe for a smaller school, I end up with a shorter run. I don't get to flip 1,000 times. I only get to flip about 200 times, and I end up right around here. All right, so now if I do this across a whole district, for each school, I'm going to get a run of flips. If I do this across a whole district and sort of track where each school ends up, then I'll have like a dot for each school, and we have a different school sizes. Some schools are larger, some are smaller. And so now at this point, if I say, all right, who are our best coin flippers? Who tends to get a large number of heads? Maybe I'll draw a line at 55%, and I'll say, all right, let's look at all the schools that ended up above 55%. Well, look at that. They're all on the lower end of the range. So, all of our large schools, because in the long run, we approach 50%. So all of our large schools end up, not above this line. They all end up closer to 50% than these handful of small schools. So with the coin flips, it's not that the small schools are better at flipping heads. All the children are equally likely to flip heads or tails, but with the schools that have fewer flips, so the smaller schools have fewer flips, and those are going to tend to have the more extreme values. Larger schools are going to tend to end up closer to an overall probability of 0.5. So now if we go back to test scores for a minute, could we be seeing the same thing with the test scores? If the school size has nothing to do with the achievement, if it's like you're just as likely to do well if you're a small school versus a large school, we would still expect, just due to the sample size, the fact that we have smaller sample sizes for these small schools, we would expect more extreme values. And that's true both on the high end and on the low end. In fact, if I go back here and I look, like my top achievers in terms of coin flips are small schools, my worst achievers in terms of coin flips are also small schools. It's just that the extreme values tend to happen for the smaller samples. So this is what the most dangerous equation is. It has to do with the variability of an average, and basically, if you're allergic to the math, then it basically says we can expect more variability in sample means or proportions for small samples than large samples. And so smaller samples are going to tend to go to the extremes when there's no other or even when the school size or the sample size has nothing to do with the. So how can we avoid this mistake? Because this is a very common type of mistake. So be very cautious when comparing different sized groups. This could be if you're looking at county level data. you're going to tend to, just because of sample sizes, see more extremes in small counties. So, be cautious about that. Don't just focus on the extremes. Like, don't say, I'm going to just hone in on the top and see what's going on up there, because the top is going to tend to collect smaller sample sizes. And then also this gets at kind of the heart of statistical reasoning, which is start with a simple explanation. In statistics, that would be what's called a null hypothesis. Basically, that whatever factor you're looking at has no effect on the outcome. So if it's school sizes, you start with the assumption that school size has nothing to do with test scores, and say, and then ask yourself, is the variability that I'm seeing, can that be explained just due to sampling error? So like our coin flips, there is going to be that randomness, and we'll see those extremes at the lower end. Could that explain the variability that we're seeing, or the differences between small and large, or whatever factor that you're looking at? And so that's what statisticians do, is they say, let's start with a null hypothesis. Basically, there's nothing going on here. There's no effect. And then determine, is what we're seeing in the data, is that in line with that null hypothesis, or is the effect larger than what could be explained there? So, with the school's data, I didn't go to the raw data to check, but it sure seems like they didn't rule out that sample size might have just been the driving factor there. All right, so I've gone through three cases. I'll wrap up here. I think my overall conclusion is be careful, be cautious when you're working with data. Think carefully about the source of your data. Do I have something that represents the population of interest? Is there some bias cooked into that? Make sure you're making the right comparisons, normalizing when needed. And then finally, be mindful about sample size and sampling variability, and just understand that particularly when you're dealing with small samples, you can expect a lot of variability, and account for that, or make sure you at least consider it when you're coming up with your recommendations. So I'll stop there. I've got some sources. A lot of this 538 had some excellent articles. They've always got really great data analysis and analytics and just statistical reasoning articles. They had some really good ones about Charles Reap. But yeah, anyway, I'll stop there.